So I'm now recording on in our class meeting. Welcome everyone to our introduction to networks meeting. I'm sorry about the last couple meetings having to be canceled. I've had some rough times with physical health, but thankfully it seems like we're getting things back on track. I want to do a couple things today. First off, I do want to share and talk a little bit about chapters, although we're past them in terms of items that are due. I want to talk a little bit about Chapter 3, the concepts behind a model or a shared model. And I want to make sure that you're understanding when we talk about models and the different models for the Cisco Networking Academy Pro, or not Cisco Academy, but any type of communication, we're talking about models of how two devices communicate with one another over a network. So we need to have some way of fundamental communication. With humans, we do this automatically without really even thinking. We have the, if I look at you and go, huh? That rising inflection lets you know that I'm actually asking a question. So we have an ability to encode things into language as humans. And so we can actually do the same with a computer, but we have to do it in a more honestly, not sophisticated, not any more sophisticated than the language, but we have to make sure we spell it out very directly for computers because they're not very smart. So we're going to need a way to take a message. We're going to need to take that message and encode it in some way to send it across some medium. And then on the receiving side, have that side decode the message. That's going to require us to use rules. Now, if we don't follow rules, it's very hard for us to read something, especially in the English language or in any language. So here we have an example of using two different languages in a single message. But if we were to use a single language, we could understand it. So we need to have our rules in place. I talk a lot about the fact that with rules, there are certain rules that we follow every day in terms of, if the president of your college walks up, you're probably not going to go, hey, what's up? You're going to say, Dr. So-and-so, how are you today? So there are a lot of rules that we follow that we don't even really think about in our day-to-day world. One of the ones we do is we drive and we follow the rules of the road, hopefully. And those are rules that we have really ingrained into our minds through years of driving. And it's always interesting to see someone who is a new driver because they are very careful about things that sometimes we probably need to be more careful about. But they're very careful about every single rule and following those rules. Now, when we look at encoding and message formatting, one of the things that we need to be able to do is make sure that the sender can get the item or the data to the receiver. And this is a great analogy they use here, and this is the analogy of a letter and how the letter has information inside of it. So that's our data that we're carrying. And then that data has to be sent using a address on the envelope. So that's the destination of who it's going to, where it's going to, the source of the message. And then the encapsulated letter has all the other items like the dear, salutation, who the recipient should be, the message itself, and then finally an end of frame delimiter or end message indicator. These types of items are what we're going to need when we talk about different protocols. When we talk about TCP/IP, or as we move in our chapter for this week, which is chapter 5, Ethernet. And Ethernet is really nothing more than a layer 2 protocol that has been set up. So a little bit about, they talk about message size, message timing, talk about flow control, to make sure that both sides have the ability to listen and being able to communicate with one another. And if they talk at the same time, then obviously you're talking over each other and you won't understand one another. Some delivery options. I like this. Unicast. That's from one person or one device to one other device. Multicast is from one device to some of the devices in a group. And then broadcast is from one device to everyone in the group. And computers do the same thing. Unicast is 1-to-1. Multicast is 1-to-some. A good example of multicast is if you have a video streaming service in your network and machines can register with that video streaming service, they may be, or they will be actually associated with a multicast address that will receive those streams. And then broadcast is 1-to-all. Now, I teach my students that broadcasts are bad, and typically that is true. Having said that, though, you can't eliminate all broadcasts. There's just simply no way to eliminate them all. You just don't have a choice for some things. Okay. When we talk about the rules and we talk about items that are going to be part of our rules, we obviously need a way to speak the same language, which is what we're going to do. We need a way to encapsulate our data so that on the receiving end it can be de-encapsulated. And then we need something or some medium to put it out on. So we're going to talk about putting it out on wireless, putting it on copper, putting it on fiber optic cable. All of those are different options. We're going to talk about some of our protocols. Now, here's a protocol. Now, this is IP. In our case, we're going to work with IPv4 and IPv6, the two major network protocols in the world today. There used to be many more. There used to be IPX-SPX. There used to be, and there still is, Apple Talks out there, but nobody really uses it. Everybody uses IPv4-6 now. But we're going to have different ways to determine our paths and how to keep up with how to get from one neighborhood to another. Now, when I say neighborhood, I'm using the analogy of the letter. Now, remember, again, we have to have a destination address. The same thing is true with IP addresses. IP addresses are how we actually go across the internet to get to our destination. Right now, my PC is sitting at my house, and it is on the local network. So if I do CMD into an IP config, you're going to see I'm on 192.168.12 dot something or 254 dot something. So I'm on my wireless LAN right now. Well, this is going all the way across the internet up to the Zoom servers, and now it's hosting that information. So to the Zoom servers, this is my IP address. If you go right now on your PC, go to your PC right now and check your IP address and see what you got. Let me know what it is. Just, you can drop it in the chat or come off of mute. So mine was 192.168.254. Anybody else? What you got out there? Again, to do that, you can go to your search bar and just type CMD for command, or you can do, if you're on an older version of Windows, you can do start and then do run and do CMD. And you'll get a command prompt and type ipconfig, and it should give you your IP address right there. You'll notice it is in dotted decimal format, so mine is 4 sets of up to 3 decimal digits, values from 0 to 255, although 255 will not be a value. So we got somebody with a 192.168.1. Anybody else? Most of you, I can about guarantee you everyone's going to have 192.168.1 or .0 or .254. Those will be the ones that you're going to have. Anybody else? Lena, you got yours?
Yes, 192.168.09. It's IPv4.
Yep, 09, that's exactly right. Most of our home routers use 192.168.0 or 192.168.1. Or 192.168.254. So our home numbers, we'll learn very shortly that those numbers are what are called private IP addresses. So those addresses cannot be routed across the internet. So we're being NATed or network address translated in order to get out on the internet. So that's very important. Excellent. So when we look here at these different models, now this is a model. This is what is called the TCP/IP model. And one of the things I want to do is I do want to turn on here just a second if I can find it. And of course I can't find it, so I'm in trouble here. Let me see. Oh, there it is. All right. This, folks, is a little model of an airplane. Take a peek at it. All right. This is one of my other hobbies. This is a Aeronautical Imperialis from Warhammer 40K. So it's a little model. See the little bombs on it and everything. This model has about, I'd say, 20 parts on it. However, what if I went to make a real one of these or a real airplane and wanted to go and make it fly for real? How many parts do you think a real F-16 has? You know what an F-16 is? It's a fighter jet, U.S. fighter jet, one of them. Or an Fa-18, that's one of our modern Navy fighters. It has millions of parts. So when you think about a model, and this is what we're going to discuss in this section, we're going to talk about two different models, the OSI model and the TCP/IP model. This TCP/IP model has 4 different parts that are used to describe how two devices talk to each other over the internet. But they're not the be-all, end-all. They're not exactly how everything works on the network. Now, I will say this, the TCP/IP model is considered to be what they call a protocol stack model. So it's closer to the way things really occur than the OSI model. The OSI model is more of a true theoretical model. So with our device here, with our TCP/IP model, we've got the application layer, and that's the layer that provides services to all of our application protocols like HTTP, DNS, and others. The transport layer, which is the layer that provides guaranteed reliable delivery typically, but then we're going to also learn that the transport layer supports both TCP and its little brother UDP. And then we've got the internet layer, which is how guaranteed things can be routed and are delivered. Well, it doesn't actually guarantee delivery, but it is how things are routed across the internet. And then finally, we have the network access layer. And this is the layer that defines, in the OSI model, we'll learn that this is layer 1 and layer 2 items. Okay. I wish I had I don't have my pen set up to take my pictures. Let's see here. Oh. So here it is, Application Transport Internet Network. A way to remember this is to remember @n or ATIN, ATIN, or @n, either one, but you will need to remember the 4 layers of the TCP/IP model. And you'll see the different protocols that work at these layers. So HTTP, DNS, DHCP, FTP. By the way, HTTPS would also work at the TCP/IP application layer. TCP and UDP are at the transport layer. One of them, TCP, provides guaranteed reliable delivery. UDP does not. It is unreliable delivery. I always call it TCP's unreliable little brother. Internet is how you do your routing, IPv4, IPv6. And then last but not least, you have network access, which covers the 2 different layers of layer 1, layer 2 of the OSI model. Now, the beauty of how this is designed and was designed is the network access layer. Nothing was actually ever absolutely stated at the network access layer for IPv4. So you had a setup to where you could go in and run TCP/IP on anything. It'll run on Ethernet, it'll run on PPP, frame relay, X.25, ATM, wireless LANs. There's even a fictitious joke protocol that is TCP/IP over carrier pigeon. So, you know, that's pretty funny, but it is actually out there as a possibility, as a joke. We have other things today. Obviously, we now have faster versions of Ethernet. We have 10 gigabit, 40 gigabit, 100 gigabit Ethernet. All of that can support or can run on TCP/IP because the inventors of TCP/IP did not set anything to be the basis for layer 1, layer 2? Absolutely. Which is a great thing for TCP/IP. Any questions about that, about TCP/IP? How long has it been around? Well, it's been around since the 60s, to give you an idea of how long TCP/IP has been around. And IPv6 has actually been around a very long time too. So it's amazing that IPv6 has been around as long as it has, and we have not moved to it. So it's been around since 1995. We have not moved to it yet completely. I like to tell people, if you see things 3 times, well, let's see, we've seen 1, 2, 3. You know it's going to be on the test, okay? And you can look at the different types of protocols here, and it actually, as you click on them, it will tell you what each one of them is. All right. So TCP/IP, there's an Ethernet header. Now, we'll learn, and you have learned in Chapter 5, that an Ethernet header consists of, obviously, the starter frame delimiter. It consists of the destination MAC address, source MAC address, and then the protocol that's being passed up to. And then there's an IP header, and that header is the source and destination IP addresses. So if I was to send something to one of you, then, in fact, good example here, Amy's IP address was 192.168.1.38. Mine was 192.168.254.66. If I was to send a ping to Amy's PC, it wouldn't work, folks, because of the fact that we're on private IP addresses. But let's just say we were on a network where it would work. The source IP address would be my IP address right here. The destination IP address would be Amy's.38. If I do an IP config/all, you can actually see the MAC address for my machine that would be sent over using the Ethernet headers. You then would have another header at the transport layer, and that header will either be TCP or UDP, depending on what particular application layer protocol you're using. And then the next item would be the data, and that's your application layer protocols and information. So if I was, for instance, if Amy was pulling a web page off of my machine, that would be an HTTP. It would be a get from her, it'd be a push or a send from me, one of the two. And again, once again, here's the 4th time we've seen it. So that's going to be a pretty good idea to show you where it's at. Now we have all these standards organizations, and as a result, they came up with another standard that they call the ISO standard. And that standard is the OSI model. It also is called the 802 standard. I believe it was originally formed in February of 1980. Don't let a bunch of drunk network engineers get together at a conference or you'll get something like that. But we have here the OSI model, the application, presentation, and session layers. By the way, they perform the functions associated with just the application layer of the TCP/IP model. Now you need to know this, and your students need to know how these two map to each other. This OSI model is definitely more theoretical than the TCP/IP. TCP/IP just kind of lumps everything the application, presentation, and session layers do together because that's how it works in the real world. They're kind of just all lumped into that application portion. Whereas the OSI model says, no, the application layer provides services to applications. The presentation layer converts data into intermediary formats in the event that they need to be in intermediate formats, and they provide compression if needed. The session layer establishes, maintains, and quits or stops sessions between entities. And then all of that's what the application layer does in the TCP/IP model. The transport layer and the transport layer on the TCP/IP model, they perform the same function. They are designed to provide guaranteed, reliable delivery, unless, of course, you're using UDP. Network layer and the internet layer provide the same function. In other words, they are responsible for routing and for path determination. And then you've got the data link and the physical. Now, the data link layer is where things go from being hardware to being software. In other words, your network interface card is where you would consider the data link layer to be at, because it's actually got 2 sublayers. One of them is called the logical link control, and LLC sits right below the network layer and talks to the software of the network layer. And then you got the media access control, or the MAC layer, which sits a little bit lower and talks to the hardware of the physical layer. So here's what I was talking about earlier. The TCP/IP model is a protocol model, so this is how the protocol actually works, whereas the OSI model is a reference model, or more of a theoretical model on how you describe things work between the communication, not necessarily exactly how it works. Are there any questions at this point about OSI model or about the TCP/IP model? All right, got a question here. And feel free to come off. Oh, no questions, okay. Feel free to come off chat if you need to. But the application layer contains layer protocols for use in process-to-process communication. Hopefully my internet's gonna stay stable enough. Presentation layer provides for common representation of data, so it converts it into intermediary formats or provides compression and encryption. Session provides services to the presentation layer to organize its dialogue in order to manage the data exchange. Transport layer defines services to segment, transfer, and reassemble the data for individual communication between end devices. We'll learn a great deal about segmentation, windowing, retransmissions, sequence numbers. All of that is part of what the transport layer does with TCP especially. Now with UDP, it still segments, but it doesn't do all the retransmission items. Network provides services to exchange your data between different networks. Data link methods for exchanging data frames, and frames are important here. That's an important word. And then physical is how you get it onto the actual entity, so bits. So there's also a thing called a protocol data unit at each layer. And we consider the physical layer, its PDU is bits, data link is frames, network is datagrams, typically datagrams, and then transport is segments. So, and then you see here, this model is our protocol model. We talked a little bit about that already. We've already done that. There's our comparison for the 5th time. So make sure you know that. You will be asked that somehow on a test somewhere, either a chapter exam or a real exam somewhere. And here's something else you can do. All people seem to need data processing. That's how you can remember the OSI model from layer 7 to layer 1. All people seem to need data processing. If you want to remember it from layer 1 to layer 7, please do not throw sausage pizza away. So there's 2 different mnemonics that you can use to remember the different OSI model information. All right, segmentation, wait, let me show you protocol data units. Here they are. So it's bits, frames, they call it packets or datagrams. So you see it in different ways depending upon what particular book or piece of information you're looking at. But it's bits, frames, packets or datagrams, and segments. And then everything else is just called data. And here's an encapsulation example, again, being encapsulated on the sending end. So you want to get a web page, or you want to send a web page from the web server. That's the data. You're going to get a TCP header on it. You're going to get an IP header, which has source and destination IP addresses. And then you're eventually going to get source and destination Ethernet or MAC addresses, because those are layer 2 addresses. And then you will have a frame trailer or CRC, which will end the frame. Now, when it gets turned into 1s and 0s, it goes over to the client, and the client will then decode that based upon the type of protocol that's being used on the network. And that's for every single piece of information that is sent across the network. So it's really kind of amazing that any of this works at all. It's very amazing that it works as fast as it does, because it isn't there's a great deal going on to get something sent between 2 different machines, even just something as simple as a web page, because this isn't even covering DNS lookups and all the items that have to take place before we ever start the encapsulation and de-encapsulation process. All right, so network addresses. One of the things I want to bring up now is all these different types of addresses. So we do have our data link addresses, which are physical. Those addresses are burned into the MAC address. Now, you can spoof MAC addresses. It is possible. But for the most part, they're burned into the MAC address, or burned into the NIC, and they're hard to change. Hard to actually change on the NIC. They're not hard to spoof. The IP addresses are called logical addresses. Those addresses are logical because there's no reason why I'm 192.168x versus 192.168y. It just happens to be that's what my home router uses or what I set my home router up to. It makes no difference whatsoever. Just like at your work, you're probably 10.0.0 something or 10.0 1 dot something in your particular network, simply because that's what we use in our networks. So they are logical. They're not based upon anything physical. Data link addresses are physical addresses because they're based upon the MAC address on your NIC. In this case, we're showing here 2 layer 3 IP packets. So 1.100 going to 172.16.1.99. That's just 2 separate networks. You will learn again that both of these are actually RFC 1918 addresses. So they are in fact non-routable across the internet, but we use them in the labs because of that reason. And then here we see the destination NIC, source NIC. So it'll be destination MAC address and the source MAC address, source IP, destination IP. And the reason, by the way, you'll learn as we've looked in Chapter 5 at Ethernet, you'll learn that the reason the destination MAC address is first is because traditionally every machine had to look at all the frames going by it on a bus network. And so they could look at it very quickly and say, is this my MAC address? And if the answer is no, they just discard that frame. If the answer is yes, then they had to bring that frame on up to layer 3 and start, or only up and break it apart and start de-encapsulating the entire frame. So that's because of traditional Ethernet and the traditional bus networks. Have any of you ever worked on a bus network before? Have you even seen a bus network or know kind of what it is?
I have not.
Okay. In the old days, we actually used Ethernet over RG58, 58 or 59, maybe 59. But either way, it was like the cable you have for your Time Warner cable or Spectrum cable now. It was, you use taps or T's and you put it in. So we'd actually have a physical bus of the cable. It was not fun to work with. You had to put actual endpoints, or you had to actually put a, oh God, I can't remember. I'm drawing a blank on what name of it is, but you had to put on the end of the line to make sure signals wouldn't bounce. So it was a real pain. Today we run pretty much star wired buses. So in other words, we're running them as stars off of switches. So we'll talk more about that as we move forward too. But this is a star here. So you can see how the devices are coming off of the switch. Each one has its own connection to the switch. So that's a nice thing. Communicating within the same network is a lot easier. Well, not easier, but it's the simple process here is when you need to do what's called a request for your MAC address, or an ARP request. That ARP request can be flooded throughout the switch, and the actual device can return its MAC address. So before you can send out anything to another device, even if you know the destination IP address, you must know the destination MAC address. Otherwise, you can't create a frame. If it's local, okay, so if you're communicating with a device on the same network, you just send out what's called an ARP request, or an address resolution protocol request. And then the device that has that MAC address will respond, and you build your frame. If it is not a local device, then what happens is you send out an ARP request, and then your default gateway will respond with its MAC address, so that you will create the frame that will send it to the router, and then the router can send it on to the next hop. This is called Proxy Arp, because you can't, by default, pass any type of broadcast past a router. So when the ARP request comes in from PC1 going, hey, who has 172.16.1.99, the router or your default gateway sees that that is actually a remote device and says, oh, that's me, send it to me. and then it will come over to router 1, and R1 will then look in its route table, make a decision about where it needs to forward it, and will then forward it if necessary. So this is Proxy Arp. It's the process of a router using its MAC address in place of a remote IP address's MAC address. Very, very, very important concept here. Any questions? None? Okay. Good. So one of the things I want you to be careful with is make sure when you are doing the labs and net labs, make sure you're not using, do not use the documents inside of the curriculum. You must use the documents inside of net labs because they do not match up. I've had some folks have some problems with that. So please be aware that you need to use the documents inside of net labs, not the ones in the curriculum, to do your hands-on labs in our netlabs.stanley.edu site. All right, any other questions before we move on? Just kind of quick look at chapter 4, and then we'll roll in chapter 5. Anybody? All right. I'm just going to very quickly just blow through chapter 4. It's about physical connectivity using wired versus wireless Ethernet. By the way, you saw when I showed you a little bit earlier that a wireless and a wired Ethernet card both have a MAC address. And in fact, you can have your wireless card on your machine and a wired card. So be aware you could technically be connected with 2 MAC addresses. I do want to warn you, if you use laptops in the labs, or if you're doing anything with the labs and you plug in like a USB dongle and you're doing labs, but you're also still connected or trying to connect to the wireless network, make sure you turn off your wireless NIC when you're connecting to work on the labs. And by that, I mean like your students are working on the labs in your classroom. You know, they got a laptop, they plugged it in physically on the wired NIC to the switch. If they still have their wireless NIC on, that can cause issues with the routing because they're going to have a default gateway that goes out through your campus network, and it may try to go that way and things just won't work correctly. So if you're using laptops for your student PCs, make sure they turn off the wireless while they're doing the physical labs. So here we have it again. We have the OSI model. We're going down, we're encapsulating the data. So we got segments up at transport layer, we got packets or datagrams at the network layer, we got frames, and then we got bits. So at the lowest layer, we're going to have bits, 1s and 0s. Now, those can be represented in multiple ways depending upon what type of medium you're using. If it's copper, it's going to be, it can be the presence or absence of a particular voltage. It can be it can be a particular voltage being met, like +5 volts, or it can be the fact there is any voltage on the line at all. It can be light pulses. In other words, is there a pulse? Isn't there a pulse? So if there's light on the line, then that's a 1. If there's not, it's a 0. It can be all different types of things depending upon what type of media you're using. When we look at our different types of media, copper is our cheapest for the most part. Copper or wireless are our cheapest. Fiber-optic is the best for being able to survive any type of electromagnetic interference. It's also the most secure because it's very difficult to pull any type of information off a fiber-optic cable without breaking it. Now, am I going to tell you that there's not some type of super secret CIA thing that could pull information off a fiber-optic cable without cutting the cable? No, I mean, I'm sure that's there. But for the most part, it's a lot harder to do. Copper cable, you can actually lay a device right beside the copper unshielded twisted pair and just pull the information right off of that. So it's not a big problem. And wireless, obviously, is the easiest to get because it's just flying around everywhere with signals. That's why you have to encrypt it to make sure it's not just pulled. So some physical standards. We talk about some different ways of connecting things. You don't do as much of this in this particular class, but we do when you're working on your own computers and labs. You're going to be working with different types of Cisco connections. Some of those will be our obviously unshielded twisted pair cabling, shielded twisted pair. You're going to have V.35 cables, which connect to smart serial connections on the Cisco devices. So you will need to review some of that when you go back to working in your actual classroom. That's the only negative this format has, is I can't literally hand you cables and say, here, this is this type of cable, this is that type of cable. But you'll be able to do that in your own classrooms. Here's Manchester encoding, where the transition in the middle of the bit period. Now, one of the things about encoding that's important is notice that it's always some value during a period of time. So this Manchester is, if it changes during a period of time, then it's a 1 or a 0. Okay, or it changes versions. I gotta see what I got. So it changed, let's see. So nothing changes there, it changes. That depends on that one. I forget what Manchester does exactly. The presence or absence of the voltage should give you your thing, but you're looking at a change over time. So that one changed. Okay, it stayed the same, so you get the voltage. Nope, that's not it either. I had to figure out this looks a little weird to me on the Manchester. Typically, we're looking at different heights or different values, and those values will be, will give you a 1 if it's on, a 0 if it's off. You also have the ability to look at this. You can look at modulating FM or amplitude modulation. You can look at the different number of waves in a particular time frame. So signaling method is what we're looking at here. So, oh, okay. 0 volt, 0 bit by high to low volt transition. Okay, so that's how 0 is. So 0 is a high to a low voltage transition. And a low voltage to a high transition is a 1. So that makes sense. So here's a transition to a high, that's a 1. Transition to a low is a 0. Transition, that should be a 1 right there, though. That's what it looks like to me. And then down to 0, I guess it's because it transitioned during that time frame. That's why it's a 0, because it transitioned during the time frame. Transitioned, yep, that's it. So if it's transitioned to a high voltage, it's a 1. If it's transitioned to a low voltage, it's a 0. So that's what it did here during this time frame. It transitioned to a low voltage, so it's a 0. There's all different types of encoding. I am not, by the way, the world's best electronics person. That's not my specialty. I turn it in. If it doesn't turn green, I try another cable. So that's kind of where I'm at with electricity. This is important because bandwidth is the maximum capacity of a link. And one of the things I want you to realize is bandwidth is not how much it's actually carrying at any one time. Bandwidth is the max it could carry, all right, in a given amount of time. So we've got, basically, if you look at bandwidth, bandwidth is the amount in the garden hose. Let's say you have a 4-inch pipe. Bandwidth is 4 inches of water, all right? Throughput would be the amount of water going through the pipe at that time. So it may be 2 inches worth of water in a 4-inch pipe. So your throughput's 4 inches worth of water. You then have another concept called goodput. And goodput is the data that is being sent without any of the control headers or any of the control data. So you almost never have an instance where your throughput and your bandwidth are the same. It just doesn't happen. You're going to have retransmissions, you're going to have errors, you're going to have control data and things that have to be used. So the throughput is what's currently flowing through your media. Bandwidth is what theoretical max of the media. And then goodput is the amount of usable data, not controlled traffic going across the media. So here we see some different interfaces on a Cisco 1900 series router. We've got RJ45 Ethernet connections. We've got RJ45 fast Ethernet ports. You got what's a SHDSL, so a synchronous high density link here. You've got some USB ports. Those are all different little ports there. They got some physical topologies there on that. Here's characteristics of copper cabling. One of the things you need to realize is that copper cabling does have susceptibility to EMI, or electromagnetic interference. It also has susceptibility to crosstalk, and that is signal interference from adjacent wires. That's why we actually use shielded twisted pair and unshielded twisted pair. Twisted pair, the whole concept in a twisted pair cable is for the twist to be different between the pairs to reduce crosstalk between the pairs of cables. The other one they don't mention right here, but it's called attenuation. And attenuation is the loss of signal strength the further a signal goes along a line. And that's usually due not to interference, but it's actually due to the impedance of the particular type of cable you're sending things across. So we've got attenuation, the loss of signal strength as it flows along a media or medium. We've got EMI, and that's electromagnetic interference from outside of the cable. And then crosstalk, which is interference from adjacent pairs of cables. In order to make sure we are okay, we have to follow the rules of our cable. Unshielded twisted pair can go a maximum of 100 meters, which is 328 feet. Shielded twisted pair has the same basic limitations of 100 meters, but it can be a little more resistant to EMI. And then coaxial, there's different types of coaxial. There's 10 base 5, 10 base 2. 10 base 2 will go 185 meters. 10 base 5 will go 500 meters. That's thicknet, which is what we're basically using with our satellite systems in our houses this day and age. You'll notice here this coaxial cable does have a shielding around it, or it also really is more used for a ground than a shield. Now here's shielded twisted pair. This is actually used to shield. And if you look close in these pictures, you can actually see it right here. You can see how the brown pair has less of a twist than the green pair, which has less than the orange and white, which has less than the blue and white. And so all of these cables are twisted at a different rate to help with crosstalk, the possibility of crosstalk. And if you rip off the cabling on an unshielded twisted pair or a shielded twisted pair, you will see the same thing. You'll see a different rate of twist. Here we have our twisted pair, outer jacket, all those there. Shielded twisted pair. Typically, you can have a braid or full shield around all of them, and you may even have full shields around each individual pair, depending on which one it is. And that really helps with the EMI and crosstalk. So we'll help with crosstalk too. And here's our coaxial using a BNC type connector or an F-type. F-type is what we use with our satellite TV and cable now. BNC is what we used to use when we were using our true bus networks. And that stands for either bayonet connector or British naval connector, depending on when I'm talking to somebody who is a British sailor. Safety for copper media. One thing is, copper is a great conductor of electricity. Therefore, you must be careful about things such as potential differences in large buildings. So if you tried to run, on a very high story building, 10, 20, 50 stories, if you had copper cable and you were using that, there can be a difference in the potential charge from one to another, and you can actually have a problem with electricity flowing across the copper cable and killing somebody. So between levels on a building, we use fiber optic. Between buildings, we use fiber optic. We're even getting now to where we use fiber optic inside, just in the data center, just because it's cheaper and easier than using some of the 40 gig and 100 gig copper cables. All right. Again, some of the standards. We got category 3, which is only rated for phone lines. It'll actually do up to, I think, 4 megabits per second, 3 or 4. Category 5 and E will do up to 1,000 megabits per second. And Cat 6 UTP, actually, they recommend shielded twisted pair to be able to do between 1 gigabit to 10 gigabit. Although it's not necessarily recommended, but we've been seeing a lot more stuff with 10 gigabit copper connections coming in, especially servers with 10 gigabit copper NICs on them. And here's our different cables, RJ45. That's definitely a bad cable. You'll notice there's no, the shielding is, or the sheath is not up in the connector to help provide strength. This will eventually pull out and you'll have, drops, and you'll have problems, you'll have opens. There is in this particular thing a lab to create cables. So That's good that you need to do in your classroom. Here we have 568A and 568B. These are just two different standards to where you can see white, green, green, white, orange, blue, white, blue, orange, white, brown, brown. I typically use 568B, white, orange, orange, white, green, blue, green, white, brown, brown. And if you put the same standard on both sides, you get a straight through cable. Okay. If you put B on one side and A on the other, you flip pairs 1 and 2, you get a crossover cable. And if you flip the whole thing, literally put the tab one way away from you on one and towards you on the other, in fact, this should be, the tab should be away, not towards you, then it's a rollover cable. And that's what's used to connect to the console port on a Cisco device, is a rollover cable. That's what that ugly Carolina blue cable is. Sorry, I went to NC State, y'all. So every time I see one of those Carolina blue cables, it gives me the weebies. So here we can say 568A. You can do white, green, green, white, blue, blue, white, green, green, white. Nope, take that back. White, green, green, white, orange, blue, white, blue. That nabbit. Wrong way. Orange, brown, brown. See if I got it right. Correct. Got it. And then they got you one for 568B. So did the pinouts there, which is good. And then there's a lab building this. Now, this is not one I can do in our online class, but I do want you to try to do it in your own lab at home or at school. Build your cable and test it, because this is a good lab to have. Now, I will say most of us now buy our cables, but still, it's a good thing to have. Do either one of you have fiber optic cable to your house? Either one? I do not. I wish. Question, will we have to know the cable layout for the exam? Yes, I would know that. I would definitely know that. Fiber to the home is getting more common. It is not widespread, but it's getting there. Fiber optic cables are designed to have a jacket, strengthening material, a buffer, cladding. Typically, they've got in here some type of Kevlar to provide strength, and a glass core. It used to be, we would say that the core was plastic for short range and glass for longer range, but the truth is it's pretty much the same for both now. It's both glass. We have single mode, which is a glass core of 9 microns. It can go for very long distances using lasers as the emitters. So it can go, you know, miles and miles and miles and miles and miles, depending on how strong the lasers are. Multi-mode typically still has a glass core, but it's 50 microns. And it does use, in some cases, LEDs for emitters, but most of it, all of it now is going to be lasers for emitters, just because it's what they've gone with. We use multi-mode for shorter runs, like inside of a data center, or maybe even between buildings, depending on how close the buildings are to one another. Some different connectors here. Here's how I describe these. The ST connectors, I call them simple twist, because you push them on and twist them. Okay, you know, they call them straight tip, but I call them simple twist. You push those on and twist them. The SC I call simple click, because they click in. You pop them in, they'll click. You got the LCs. These are lucent connectors, which are smaller version of the SCs. And in fact, most of what we got now are these duplex lucent connectors, and they still click in. So light click, I guess you could say. Simple click and light click might be what we could say there. But these simple twists, those are the older style, and we don't typically use those much anymore. And we got different types of patch cables. Here's a simple click, or SCSC. And there are more types of fiber optic cables than you can shake a stick at. Here's a couple things here you look at testing fiber optic cables. One thing I would tell you, never ever look into a fiber optic cable for any reason. Do not put it up at your eye. If the LED or even the LED or laser was on the opposite side, it could immediately destroy your eye. So don't ever look in one. Don't even put it on your hand to see if you can see something through it. You know, some people put a flashlight on one side to see if you could see it through. I wouldn't do that because somebody could hook it to the laser, and next thing you know, you're burning a hole in your hand. The best thing to do would be to get you an OTDR, or optical time domain reflectometer, and use the OTDR to do your testing. So, and they do talk about using a bright flashlight into one end while observing the other. I mean, that'll work. There's no doubt it'll work, but I'd be careful of that. I'm just not a big fan of teaching students that. Fiber versus copper. Copper's cheap. Copper's easy to install. Copper has very little resistance to EMI, very little resistance to electrical hazards, whereas fiber optic cables can run, really, we don't even know what the speed is. The max speed on fiber optic cable, obviously it's speed of light, but we don't know how much it can carry in terms of bandwidth because we're limited more by what we can push across it than what can be carried by the fiber optic. It is completely resistant to EMI and immune to electrical hazards. That's why the place my dad used to work was a big aluminum plant, and they had to run a lot of their gear, a lot of their stuff in the pot room. They had to run it with fiber optic because of the fact that the pots created such a huge amount of EMI. All right, right now wireless is not as big a deal in the curriculum, but it's going to become it. So we'll talk more about that as we move forward. I do want to just hit real quick on the two sublayers, the logical link control, which is that layer that provides the link between the hardware of the data link layer and the software of the network layer, and the MAC, media access control layer, which defines how media access is to take place. And we'll talk about that more as we move forward, and we talk about how Ethernet shares the media. All right, I'm going to stop right here. I'm going to stop sharing my video and ask do you have any questions for me right now? Any questions for me, anything at all?
I do not have any at this time.
Okay, I'm going to